Welcome to the PCAT Organic Chemistry Review video. In this video, we're going to try to cover the most important topics in Organic Chem 1 and 2. So let's begin. Let's get right into it. So now let's go over functional groups. So this is an alkane, and you need to know the alkanes up to 10 carbons at least. Methane is CH4, it has 1 carbon. Ethane has 2 carbons. Propane has 3. Butane has 4. Pentane has 5. Hexane is for 6. Heptane is for 7. Octane is for 8. Nonane is for 9. Decane is 10. So here we have an alkane that has 5 carbon atoms, so this is called pentane. Alkenes have double bonds. So the functional group here is an alkene. And we have a total of 6 carbon atoms. So this is hexene. Now the double bond is between 2 and 3. So we got to pick the smaller of the two numbers. So this is going to be called 2-hexene. Now what about this molecule? What's the functional group that's on it? Let's say if there's a triple bond. So this is called an alkyne whenever you have a carbon-carbon triple bond. And a triple bond is between carbons 1 and 2. So because the parent chain has a total of 7 carbons, rather than saying heptane, it's going to be heptyne. But because the triple bond is on carbon 1, it's 1-heptyne. Now, what functional group do you see here? So whenever you see an OH, it's called an alcohol. Alcohols are polar molecules. They contain hydrogen bonds, so they're very soluble in water. Now, what type of alcohol do we have here? Is it a primary alcohol, a secondary alcohol, or is it a tertiary alcohol? So look at the carbon that has the OH. This carbon is attached only to one other carbon atom. So therefore, we have a primary alcohol. Now, how can we name it? So this alcohol has 4 carbons. So instead of saying butane, it's going to be butanol. And because the OH group, the hydroxyl group, is on carbon 1, it's called 1-butanol. Now, what type of alcohol do we have in the following 2 compounds? So identify the alcohol as primary, secondary, or tertiary, and then name it. So look at the carbon that has the OH. This carbon is attached to 2 other carbons, so therefore we have a secondary alcohol. And if we count the carbons of the parent chain, there's 5 carbon atoms, which is pentane. So instead of saying pentane, it's going to be pentanol. But specifically 2-pentanol because the OH is on carbon 2. Now for this one, the carbon that is directly attached to the OH group has 3 other carbon atoms connected to it. So what we have here is a tertiary alcohol. Now the common name for this alcohol is tert-butyl alcohol. So that's the common name. What about the IUPAC name? So let's redraw tert-butyl alcohol. So we have 3 carbons, another one, and an OH group here. So if we count the longest chain, this is going to be 1, 2, and 3. So we have a methyl group on carbon 2, and we have an OH group on carbon 2 as well. So it's going to be called 2-methyl 2-propanol. Because the parent chain has 3 carbons, we need to use the word propane and add the suffix ol to it. So it's 2-methyl 2-propanol. Now, how would you classify these molecules? So these are cycloalkanes. So on the left, we have a 3-carbon ring, so it's called cyclopropane. Now the next one, which looks like a box, it has 4 carbons, so it's called cyclobutane. And then the other two are cyclopentane and cyclohexane. 3-carbon rings and 4-carbon rings are not very stable. They have a lot of ring strain. 5-carbon rings and 6-carbon rings are stable because they don't have that much angle strain. For a typical carbon atom, which has 4 bonds, the ideal geometry is tetrahedral, and so the bond angle is usually 109.5. Whenever you have a 3-sided figure, the interior angles is 180, or it adds up to 180. 180 divided by 3 means that the interior angle of cyclopropane is 60, which is very far from the ideal angle of 109.5. And so that's why cyclopropane has a lot of ring strain. Now, if you ever want to calculate the sum of the interior angles of a polygon, it's n minus 2 times 180, where n is the number of sides. So for cyclopropane, it's 3 minus 2, which is 1 times 180. All the angles must add up to 180. For cyclobutane, which has 4 sides, it's 4 minus 2, which is 2, and 2 times 180 is 360. So because there's 4 angles, if you divide each of them, if you divide the total interior angle of 360 by 4, 360 divided by 4 is 90. So each interior angle is 90, which is still pretty far from the ideal angle of 109.5. So cyclobutane has a significant amount of angle strain. Now for cyclopentane, the sums of the interior angles is going to be 5 minus 2 times 180, since cyclopentane has 5 sides. Now 5 minus 2 is 3. 3 times 180 is 540. If you divide 540 by 5, the interior angle is about 108, which is very close to the ideal angle of 109.5. So cyclopentane has a small amount of ring strain or angle strain, but not much, so it's fairly stable. The chair conformation of cyclohexane has 0 ring strain. Cyclohexane is one of the most stable of the cycloalkanes. And then you have cycloalkenes, where you have a double bond inside a ring. And this is simply a cyclopentene. Not pentene, but hexene, because there's 6 carbons. Now the next functional group that we're going to talk about are the ethers. So an ether is basically an oxygen that's between 2 carbon atoms. So whenever oxygen has 2 bonds, it usually has 2 lone pairs. So how would you name this ether? So we have a methyl group on the left and a methyl group on the right. So there's 2 methyl groups. It's called dimethyl ether. So for this compound, we have an ethyl group on the left and an ethyl group on the right, because ethyl is associated with 2 carbons. So this is called diethyl ether. Now, what if you have an unsymmetrical ether where one side is different from the other side? So the left side, we have a methyl group, and on the right side, we have an ethyl group. So to name it, we have to put it in alphabetical order. So it's going to be called ethyl methyl ether. Now what about this compound? What's the functional group? So this is called a ketone. Ketones and aldehydes, they have what is known as a carbonyl group, which is a C double bonded to an oxygen. And so there's a lot of reactions associated with carbonyl groups. But this is called a ketone. If the carbonyl group is in the middle, it's a ketone. If it's at the end, it's an aldehyde. So let's say if you have this structure, CH3, CO, CH3. How would you draw the Lewis structure? So on the left, we have a carbon that is attached to 3 hydrogens. Now, carbon likes to form 4 bonds. And we have a carbonyl group in the middle. Oxygen likes to form 2 bonds. And then we have another CH3. So that's how you draw it. And so that's a ketone. Now, this particular ketone, we have 5 carbons, and the carbonyl group is on carbon 2. So instead of saying pentane, it's 2-pentanone. So the suffix for ketone is ONE. Now, what about the ketone here? How can we name the 3-carbon ketone? What's the common name and the IUPAC name? The common name is acetone, which is found in nail polish. Now, the IUPAC name is simply propanone. Now, for a 3-carbon ketone, the only place you can put the carbonyl group is on carbon 2. If it's on 1 and 3, it's going to be an aldehyde. So you can't put it on 1 or 3. So you don't have to say 2-propanone. You could simply say propanone for this particular example. So now, how would you name this compound? So this is an aldehyde, and like a ketone, it has a carbonyl group, but it's at the end. Now, because the carbonyl group will always be at the end, if the aldehyde has the highest priority, you don't have to number it, because it's always going to be on carbon 1. So therefore, this is simply called butanol with an AL. And you don't have to say 1-butanol because it's already assumed that the carbonyl group will be on carbon 1 if it's an aldehyde. So aldehydes usually have this formula. Whenever you have a condensed structure, if you see CHO, it's an aldehyde. So the carbon is double bonded to an oxygen and single bonded to a hydrogen. So there's a trend. Let's consider carbon, nitrogen, oxygen, and fluorine, and boron as well. Boron has 3 valence electrons, carbon has 4, nitrogen has 5 valence electrons, and oxygen has 6. Fluorine has 7. So, because fluorine has 7 valence electrons, it needs 1 more to get to 8. So fluorine usually likes to form 1 bond to get that 1 electron that it needs. Oxygen, which has 6 valence electrons, needs 2 more to get to 8. So oxygen likes to form 2 bonds. Nitrogen has 5 valence electrons and needs 3 more to get to 8. Nitrogen likes to form 3 bonds. Carbon likes to form 4. Now boron, it's easier if boron gives up its 3 electrons rather than trying to acquire 5 to get to 8. So boron likes to give up its 3 electrons to form 3 bonds. So these are the usual number of bonds that these elements like to form. So carbon likes to form 4 bonds. Nitrogen likes to form 3 bonds, and it usually has 1 lone pair. Oxygen likes to form 2 bonds, and it usually has 1 lone pair. And the halogens like fluorine, chlorine, bromine, iodine, they like to form 1 bond, and they usually have 3 lone pairs. Now, oxygen doesn't always have to have 2 bonds. It's simply in its most stable state when it has 2 bonds. It can have 3 bonds or it can have 1. So, for example, in H2O, which is neutral, oxygen has its desired number of bonds. So when oxygen has 2 bonds, it doesn't have a charge. But in H3O+, when oxygen has 3 bonds, it's going to carry a charge. H3O+ is called the hydronium ion. Now, in hydroxide, oxygen only has 1 bond, and so it's going to carry a negative charge. Typically, when an element has 2 bonds, it usually has 2 lone pairs. When it has 3 bonds, it usually has 1 lone pair. And when it has 1 bond, usually it has 3 lone pairs. So let's talk about carboxylic acids. So here's an example of a carboxylic acid. Carboxylic acids have a carbonyl group and a hydroxyl group combined. Now, this particular one has 6 carbon atoms, so this is going to be called hexanoic acid. Now, carboxylic acids usually have a condensed structure that looks like this. If you see COOH, or if you see RCO2H, this is a carboxylic acid. The pKa of a carboxylic acid is usually around the range of 4 to 5. So carboxylic acids are considered to be weak acids. Now, what functional group do we have here? This is called an amine. Whenever carbon has a single bond with a nitrogen atom, you have an amine. Now, do we have a primary amine, a secondary amine, or is it tertiary? Now, the way you analyze amines is different from the way you would look at an alcohol. For an alcohol, you would look at the carbon that's attached to the OH, and you would ask yourself how many carbon atoms are attached to that carbon atom. Well, for amines, you need to find out how many carbon atoms are directly attached to the nitrogen atom. So there's only one carbon atom attached to the nitrogen atom, and so therefore we have a primary amine. Now, how would you name it? So there's 4 carbons, so instead of saying butane, is butylamine. Now, go ahead and classify these 2 amines. So both of these nitrogen atoms have a lone pair. So if it's not there, it should be there. The lone pair is also called non-bonding electrons because they're not part of a bond. However, the electrons in this bond are bonding electrons. Keep in mind, every bond represents 2 electrons. Whenever you have a bond between 2 nonmetals, you have a covalent bond. If the electrons in that bond are shared equally, it's a nonpolar covalent bond. If it's shared unequally, it's polar covalent. So, for example, the bond between 2 carbon atoms, that's going to be a nonpolar covalent bond because the 2 carbon atoms, because they're the same, they're going to share electrons equally. But let's say if you have a carbon-fluorine bond, fluorine is more electronegative than carbon, so it's going to pull the electrons toward itself. And fluorine is going to acquire a partial negative charge. Carbon is going to acquire a partial positive charge. And so you have a polar covalent bond. It's still covalent because the electrons are shared, but the fact that they're shared unequally, because fluorine is more electronegative, makes it a polar covalent bond. So let's get back to functional groups. So which one is secondary and which amine is tertiary? So this amine is secondary because it's attached to, the nitrogen is attached to 2 carbon atoms. And in the other example, here, the nitrogen is attached to 3 carbon atoms, so that is a tertiary amine. Now, how would you name it? So notice that we have 2 ethyl groups. So this is simply called diethylamine. Now, for the one below, we have 3 methyl groups, so tri is associated with 3, so this is called trimethylamine. So what if we connect a carbonyl group and an amine? What is the name of that functional group? How would you name it? So this is called an amide when you have an NH2 next to a carbonyl group. And because we have 4 carbons, instead of saying butane, this is called butanamide. Now, for the example below it, we have 2 carbons. So instead of saying ethane, it's going to be anthanamide or ethanamide. Now, this particular compound has a common name, and it's acetamide. Whenever you hear the word acetic or aceto, it represents 2 carbons, and typically there's a carbonyl group involved. Now, for the next couple of functional groups, we're not going to name it, we're just going to go over it. So whenever you see a carbon triple bonded to a nitrogen atom, this is called a nitrile. And let's say if you have an alkene directly attached to an OH. So an alkene plus an alcohol, this is an enol. Now, we talked about ethers. If you have a sulfur instead of an oxygen, what you have is a thioether. When you hear the word thio, think of sulfur. So this is an alcohol, but if we replace the O with an S, instead of being an alcohol, add the word thio, it's going to be a thiol. It turns out that oxygen and sulfur are in the same column of the periodic table. Whenever you have 2 elements in the same column, they share chemical properties. They react in a similar way. Now, the next functional group that we're going to go over is the acid chloride. So acid chlorides, they look like carboxylic acids, but instead of the chlorine, you have a hydrogen. And they're fairly reactive. So the next one is called an acid anhydride, which is also reactive. Both of these are carboxylic acid derivatives. And next you have what is known as an ester. An ester, it looks like a carboxylic acid, but instead of a hydrogen, you have a carbon. Now, this looks like an anhydride, but with a nitrogen atom in the middle instead. This is called an imide. And you might see this in the Gabriel synthesis reaction of amines. It's in the form of phthalimide. Now, this is called an imine, and you'll get this whenever you react a ketone with ammonia or a primary amine. And I'm sure you've seen this in your Organic Chemistry 2 course. This is an enamine. And whenever you react a ketone with like a secondary amine, this is the product that you'll get, or something that's like it, and that's the enamine. So now let's spend some time drawing compounds. How would you draw 2,3-dimethyl pentane? Start with the parent name, pentane. Pentane is an alkane with 5 carbons. So this is carbon 1, 2, 3, 4, 5. So on carbon 2, we have a methyl group, and on carbon 3, we have another methyl group, and so that's how you can draw 2,3-dimethyl pentane. Now what about 2-chloro-3-bromo hexane? How would you draw it? So once again, start with the parent name hexane. Hexane has 6 carbons, and I think I drew 7. 2, 3, 4, 5, 6. So we need a chlorine atom on carbon 2 and a bromine atom on carbon 3. So that's how you can draw 2-chloro, 3-bromohexane. Now what about this one? 2, 2, 3, 4, tetra, methyl, heptane. So heptane has 7 carbons. This is 4, 5, 6, 7. And on carbon 2, we have a methyl. Well, in fact, we have 2 methyls on carbon 2. It's 2,2-methyl. And we have 1 methyl on carbon 3 and another one on carbon 4. So this is 2,2,3,4 tetramethylheptane. Tetra means 4. Mono is 1, di is 2, tri is 3, tetra is 4. So feel free to pause the video and try this one. 3-ethyl, 2-methyl, octanoic acid. So octanoic acid, it's octane with a carboxylic acid. So let's draw 8 carbons. 2, 3, 4, 5, 6, 7, 8. So we need a carboxylic acid, which is always at the end, and we have a methyl on carbon 2. Now, the carbon that has the carboxylic acid is always carbon 1, so this is carbon 2. So on carbon 2, we have a methyl group, and on carbon 3, we have an ethyl, CH2, CH3. Ethyl is a substituent with 2 carbons. So that's how you can draw 3-ethyl, 2-methyl octanoic acid. So now, how would you name this particular molecule? So let's begin by identifying the parent chain. So this is going to be carbon 1, 2, 3, 4, 5, 6, 7. So 7 is the longest chain. So therefore, the parent name is going to be heptane for 7. Now, we have an ethyl group on 3, so this is going to be 3-ethyl, and we have 2 methyl groups on 2 and 4, so it's going to be 2,4-dimethyl. Ethyl comes before methyl, so it's going to be 3-ethyl. Whenever you separate a number and a letter, use a dash or hyphen. And to separate 2 numbers, use a comma. So 3-ethyl dash 2, 4 dash dimethyl heptane. Now we don't need anything in between here because we have 2 letters, L and H. We don't need to separate 2 letters. You only need to separate, you need to use a comma to separate 2 numbers, or a dash to separate a number and a letter. So go ahead and try this particular example. Now, which way should we count it? Should we count it from left to right or right to left? If we count it from left to right, it's going to be 1, 2, 3, 4, 5, 6, 7. So that means that we would have a methyl on 3 and 2 methyls on 4. So it would be 3, 4, 4. Now, if we count it the other direction, it's 1, 2, 3, 4, 5, 6, 7. We would have 2 methyls on 4 and 1 on 5. Now, you want to count it in a direction where it gives you a lower number for the substituents. 3, 4, and 4 are lower than 4, 4, and 5. So we want to count it from left to right. So this is going to be 1, 2, 3, 4, 5, 6, 7. And 7 is for heptane, so that's going to be the parent name. And we have 3 methyls, so it's going to be 3, 4, 4 trimethyl. So 3 comma 4 comma 4 dash trimethyl heptane. And so that's how you name it. So let's try this example. And let's put a bromine atom and a chlorine atom. So let's begin by identifying the longest chain. So 1, 2, 3, 4, 5, 6, 7. Is 7 the longest chain? It turns out that it's not. We can count it this way. This will be 6, 7, 8. So here we have an 8 carbon atom chain, or 8 carbon chain. And so that's longer than the 7 carbon chain. So the parent name is going to be octane. By the way, whenever you have an alkane with a halogen like bromine, chlorine, or fluorine, the functional group is now called an alkyl halide. So it looks like we have a chloro or chlorine group on 2, bromine on 4, and an ethyl on 5. So we need to alphabetize it. So B comes before C, which comes before E. So this is going to be 4 bromo, and then dash 2 chloro, dash 5 ethyl. Now we have to make sure that we've numbered it in the correct direction. So the way we have it here, we have a group on 2, 4, and 5. Now let's say if we counted it in the other direction. So let's say if this was 1, 2, 3, 4, 5, 6, 7, 8. We would have an ethyl group on carbon 4, and then we would have the bromine group on 5, and the chlorine on 7. 2, 4, 5 is smaller than 4, 5, 7. So the way we numbered it was correct. So now, let's talk about the different types of substituents that you need to be familiar with. So let's say if we have a very long carbon chain. Now, this is a propyl group, and this is an isopropyl group when it splits off into 2 directions like that. So that's isopropyl. So here, this is a regular butyl group. As you can see, there's 4 additional carbons. And to draw isobutyl, it's going to be 1, 2, and then it's going to split off at the end. So as you can see, there's 4 carbons. Whenever it's iso, it always splits off into 2 methyl groups. So that's isobutyl. Now another one that you need to be familiar with is this one, which is called tert butyl. And then this is sec butyl. And if you were to see this, that's isopentyl. So those are some substituents that you may need to know in organic chemistry. Now there's some other substituents that you should know as well. Now whenever you have multiple functional groups, let's say like a carboxylic acid, an aldehyde, a ketone, an alcohol, an amine, an ether, you need to know which groups have priority. The carboxylic acid has the most priority, and after that comes the aldehyde. Now, so everything else is going to be substituents because the carboxylic acid has the highest priority in this molecule. So, as a substituent, the aldehyde and the ketone are referred to as oxo. Now, for the amine, you would call it amino. So, and for the OH, if it's a substituent, it's called hydroxy. And for OCH3, it's methoxy because it has 1 carbon. And for OCH2CH3, it's called ethoxy. So let's say if you want to name the following compounds. Let me draw a few, and feel free to name it. So if we name the first one, this is going to be 1, 2, 3, 4, 5, 6. And the parent functional group is the carboxylic acid. So this is hexanoic acid. But we have an OH on 4, so this is called 4-hydroxy hexanoic acid. So what about the one on the bottom left? So we have a carboxylic acid again. And so it's 1, 2, 3, 4, 5, 6, 7 carbon atoms. So it's going to be heptanoic acid. But we have a ketone on carbon 4, so it's oxo. So it's going to be 4-oxo heptanoic acid. Now what about the aldehyde on the upper right? So we have 6 carbon atoms, so it's going to be hexanal. But we have an amino substituent, so it's going to be called 5-amino heptanal with an AL. And the last example on the bottom right, there's 6 carbon atoms. So this is going to be, and ethoxy comes before methoxy, so it's going to be 4-ethoxy, 5-methoxy, and then heptanal. So that's how you can name it. So now let's go over hybridization. What is the hybridization of the carbon atoms in the structure? So let's start with this carbon atom. What's the hybridization? If a carbon atom has 2 groups, it's going to be sp hybridized. Like this one, it's attached to a hydrogen and a carbon. So it's a sp hybridized. Notice that the exponents S1P1 adds up to the number of groups that carbon has. So what's the hybridization of this carbon? Well, it has 1, 2, 3, 4 groups. So therefore, it's going to be sp3 hybridized. 1 plus 3 is 4. And what about this carbon atom? It has 1, 2, 3 atoms connected to it. So it has 3 groups. And so the hybridization is S1P2. Now what about the oxygen atom? The oxygen atom is attached to a carbon atom, and it has 2 lone pairs. So it has 3 groups if you count the lone pairs. And so it's also sp2 hybridized. Now what about the hydrogen atom? It's only attached to 1 carbon atom, so if it has only 1 group, the hybridization is simply S. Now what about the hybridization of the CH bond? It's simply a combination of the hybridization of the atoms attached to that bond. So you would say it's S, sp hybridized. So what about the hybridization of this bond? So this carbon atom is sp hybridized, and this one is sp3. So you would say it's sp, sp3 hybridized. So now let's go back to this structure. What is the molecular geometry of this carbon? The molecular geometry is linear. It looks like a straight line, and the bond angle is 180. Now, what about the molecular geometry for the carbon atom? Notice that it has four groups. It's tetrahedral, and the bond angle for a tetrahedral structure is usually around 109.5. Now, what about for this carbon atom? Because it has three groups, it forms a trigonal planar molecular geometry. And so the bond angle for this structure is about 120. Now, how many sigma and pi bonds are in this molecule? Now, keep in mind, a single bond is basically one sigma bond. A double bond contains a sigma and a pi bond. And a triple bond contains one sigma and two pi bonds. So every bond contains one sigma bond. So let's count the sigma bonds first. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 sigma bonds in this compound. Now, how many pi bonds are there? Now, a double bond has one pi bond, but a triple bond has 2. So this molecule has 3 pi bonds and 8 sigma bonds. Now, what about the hybridization of the nitrogen atom? The nitrogen atom has a lone pair. What's the hybridization? It has 3 atoms and a lone pair. So does it have 4 groups? Is it sp3 hybridized? You should only count the lone pairs if those electrons are localized, if they can't move. Now, if they can move, the situation is different. This lone pair can delocalize into this bond. And so we can draw a resonance structure that's going to look like this. So now, what is the hybridization of the nitrogen atom? Is it still sp3? Because you only have 3 atoms, but you don't have any lone pairs. So whenever you have electrons that can move around due to a resonance structure, if you have delocalized electrons, you shouldn't count them towards hybridization. So therefore, nitrogen only has 3 groups, so it's sp2 hybridized. So you don't count this lone pair. It's not sp3 hybridized. Now, if the carbonyl group wasn't there, so let's say if we had this structure. Now, the lone pair can't move anywhere. So in this case, you would count the lone pair towards hybridization, and so it's going to be sp3 hybridized as opposed to sp2 hybridized. Now, let's consider the ethene molecule. So we said that a double bond has a sigma and a pi bond. Now, what's the hybridization of the carbon atom in ethene? So because ethene, the carbon atom in it, is attached to 3 other atoms, it's sp2 hybridized. So S has 1 orbital, the p sublevel has 3 orbitals. So to make an sp2 hybrid orbital, you need to mix an s orbital with 2 p orbitals, and this would be sp2. So what happened to this p orbital? Where is it? So in this double bond, there's a sigma and a pi bond. The sigma bond forms through the overlap of atomic orbitals, but the pi bond is above and below the sigma bond. So this is the pi bond, and in the middle you have the sigma bond. The sigma bond is basically the hybrid orbitals. So the sigma bond is sp2 hybridized. However, the pi bond is not. The pi bond is due to the overlap of the unhybridized p orbital, and that's basically the one that didn't mix to form the sp2 hybrid orbital. So just make sure you realize that the pi bond is the unhybridized p orbital, and the sigma bond is the sp2 hybrid orbital. So hybridization is simply the process of mixing atomic orbitals. Now let's talk about bond length and bond strength. This single bonds are long. So this is the longest bond out of the three listed. Triple bonds are usually short. However, a triple bond is stronger than a single bond. The single bond is the weakest of the three listed here. Now, the reason for that is because the triple bond has 3 bonds, whereas the single bond has 1, so 3 bonds is going to be stronger than 1. So the single bond only has the sigma bond, the double bond has the sigma and a pi bond, but the triple bond has 1 sigma and 2 pi bonds. So that's why the triple bond is stronger. But if you were to compare an individual sigma bond compared to a pi bond, the sigma bond is stronger than an individual pi bond. It's harder to break a sigma bond than it is to break a pi bond. So the next topic that we're going to discuss is something called IHD, Index of Hydrogen Deficiency, also known as degrees of unsaturation. And it's equal to 2n plus 2 minus the number of hydrogens divided by 2. So if you have an alkene, alkenes and alkynes, or anything that has a double bond or a triple bond or even a ring, are unsaturated because you can add hydrogen to it. Unsaturated compounds are not filled with hydrogen. Saturated compounds like alkanes, they're filled to the max with hydrogen atoms. They cannot accept any more hydrogen atoms. So the IHD for a double bond is 1. We can react 1 hydrogen molecule, or we can add 2 hydrogen atoms to reduce this to an alkane. The IHD of a triple bond, or an alkyne, is 2. And so we can react the triple bond with 2 hydrogen gas molecules. And so instead of adding 2 hydrogen atoms, we can add 4. So whenever the IHD is 1, for every IHD value of 1, you can add 2 hydrogens to the substance. Now for cycloalkanes with a lot of ring strain, you can react them with hydrogen gas and they will open up. So propane, or cyclopropane, has the formula C3H6, but propane has the formula C3H8. So keep this in mind. Double bonds have an IHD value of 1, triple bonds has an IHD value of 2, and rings have an IHD value of 1. So let's start with butane. Butane is C4H10. And so it looks like this. It's CH3, CH2, CH2, CH3. So carbon can only form 4 bonds. This carbon is attached to one other carbon atom, which means that it has 3 hydrogens attached to it, so it's a CH3. This carbon atom is attached to 2 other carbon atoms, so since it has 2 bonds, it needs 2 more to get to 4, which means that there's 2 invisible hydrogens that we don't see. And the same is true for this one. And the one at the end is the CH3. So we know that butane is C4H10. So if we use the formula, we should get an IHD value of 0 for an alkane. So it's 2n plus 2 minus the number of hydrogens divided by 2, where n is the number of carbon atoms. So we have 4 carbon atoms, 10 hydrogen atoms. 2 times 4 is 8, plus 2 is 10. 10 minus 10 is 0. So the IHD is 0 for an alkane. Now for an alkene, this compound has the formula CH3CH double bond CH3. So it's C4H8. So using the equation, it's going to be 2n plus 2, or 2 times 4 plus 2, minus the 8 hydrogens divided by 2. So 2 times 4 is 8 plus 2, that's 10. 10 minus 8 is 2. 2 over 2 is 1. So for a double bond, the IHD value is 1. Now, in the case of cyclobutane, each carbon is attached to 2 other carbons. So we can see that each carbon has 2 bonds, which means that they all have 2 hydrogen atoms, because carbon can only form up to 4 bonds. So cyclobutane, which is a cycloalkane, is still unsaturated. It's C4H8. And so if you add hydrogen gas to this, it's going to open up and turn into butane, which is C4H10. So cycloalkanes with a lot of ring strain can react with hydrogen gas so that the ring strain can be relieved. But cyclopentane and cyclohexane, they don't react with hydrogen gas. So let's calculate the IHD for C4H10. So it's going to be 2 times 4 plus 2 minus 8 divided by 2, or we're going to get the same answer as we did in the last example. It's going to be 1. Now for a triple bond, like a 2-butane, it's going to be CH3C, triple bond C, CH3. So it's C3H6. So using the equation, it's going to be 2 times, well, it's not C3H6, it's C4H6. So it's going to be 2 times 4 plus 2 minus the 6 hydrogens divided by 2. So that's 8 plus 2 minus 6. 8 plus 2 is 10. 10 minus 6 is 4. 4 over 2 is 2. So you can see that triple bonds has an IHD value of 2. So with that in mind, let's say if you're given a structure, what is the IHD value of this structure? So we said double bonds has a value of 1. So the IHD for this compound is 2. Now what about this example? Go ahead and calculate the IHD, or the degrees of unsaturation, for this compound. So for a triple bond, it has an IHD value of 2. For a ring, it's 1. And for the double bond in the ring, it's also 1. So the IHD value for this particular molecule is 4. And how about this example? So for the double bond in the carbonyl group, it's 1. This is 1. And for the ring, it's 1. And for this ring, it's 1, but there's 3 double bonds in the ring, so that's 3. So it's 4 for the benzene ring, 5, 6, and 7. So the IHD is 7 for this compound. So that's the main idea behind index of hydrogen deficiency, or degrees of unsaturation. So now let's spend some time talking about formal charge. The formal charge is equal to the number of valence electrons minus the bonds and dots that are in the element. That's a simplified way to get the answer. So consider the azide ion, which looks like this. Let's calculate the formal charge of each nitrogen atom in this polyatomic ion. So let's start with the nitrogen on the right side, which is the same as the one on the left side. So nitrogen naturally has 5 valence electrons. It's in group 5A of the periodic table. And in the structure, it has 2 bonds and 4 dots. So 5 minus 6 is -1. So the nitrogens at the end has a -1 formal charge. Now what about the nitrogen in the middle? It has 5 valence electrons, 4 bonds, no dots. So it has a charge of +1. The azide ion is N3-. If you add up all the formal charges, the net charge is equal to -1. Now go ahead and calculate the formal charge for each of these carbon atoms. So using the equation, for the carbon on the left, carbon has 4 valence electrons because it's in group 4A of the periodic table. And in the structure on the left, it has 3 bonds, no dots. So 4 minus 3, it's +1. So here, carbon has a plus charge. Whenever carbon has a positive charge, it's called a carbocation. Now let's calculate the formal charge for the second one. So it's going to be 4 minus, this carbon has 3 bonds, 1 dot, so it's 4 minus 4, so it's neutral. Whenever carbon has an odd number of electrons, if it just has 1 dot instead of a pair of electrons, it's called a radical. So now for the carbon on the right, carbon has 4 valence electrons, and in that structure it has 3 bonds, 2 dots. 3 plus 2 is 5, so 4 minus 5 is negative 1. So this carbon has a negative 1 charge. Whenever carbon has a negative charge, it's called a carbanion. Now let's talk about the stabilities of carbocations, radicals, and carbanions. Tertiary carbocations, that's where the carbon is attached to 3 other carbons. Tertiary carbocations are more stable than secondary carbocations. And secondary carbocations are more stable than primary carbocations. Now, why is that the case? So we can see as the carbocation has more methyl groups, it becomes more stable. So this is tertiary, this is secondary, this is primary. Stability increases towards the tertiary carbocation. Now, it turns out that the methyl group is an electron donating group, but it's a very weak electron donating group. It can donate electron density 2 ways: through the sigma bond, which is called the inductive effect, and by the overlap of atomic orbitals, which is known as the hyperconjugation. So I'm going to have to draw that on a new page. So let's say we have our carbocation center, which really wants electrons. It's starving for it. And so we have this empty p orbital. And here we have a CH3. And so let me redraw this a different way. So here's the sp3 orbital of the carbon atom, and here's the s orbital of the hydrogen atom. And so this CH bond can donate electron density by the overlap of atomic orbitals. And so that's the hyperconjugation effect. So that's how a methyl group can stabilize a carbocation center, is by donating electron density through the sigma bond by means of the inductive effect, or through the overlap of atomic orbitals by means of the hyperconjugation effect. Now, what about radicals? A tertiary radical is more stable than a secondary radical, which is more stable than a primary radical. And the reasons are similar. It's because of the methyl groups, they're electron donating groups. They can donate electron density by means of the inductive effect and the hyperconjugation effect. So carbocations and radicals, they're electron deficient. A carbocation is also called an electrophile because it's electron poor. It wants electrons. And a radical is somewhat electron deficient, but it's not always called an electrophile, but it is electron deficient, so that's why a methyl group can stabilize a radical. So that's why tertiary radicals are more stable than secondary radicals. Because they're electron deficient, they're stabilized by the presence of an electron donating group. Now for carbanions, the opposite is true. A primary carbanion is more stable than, well, let me draw it differently. So here we have a primary carbanion, and it's more stable than a secondary carbanion. And that's more stable than a tertiary carbanion. But the question is why? Why is a primary carbanion more stable than a tertiary carbanion? Now, the carbon has a lot of electrons, and it has a negative charge. So do you think the carbon wants more electrons? Because that's what these methyl groups are doing. They're donating electron density to a carbon that already has a negative charge, making it even more negative and nucleophilic. So therefore, the methyl groups, they destabilize the carbanion. They make it more negative. And so that's why primary carbanions are more stable than tertiary carbanions. Because the methyl groups, they donate electron density to the carbanion. So just to summarize what we've considered here, electron donating groups can stabilize carbocations, and electron withdrawing groups stabilizes carbanions. So let's say if we were to put a fluorine atom on this carbanion compared to a methyl group, which structure is more stable? The carbanion with the methyl group or the one with the fluorine atom? So the methyl group is going to donate electron density to the carbanion, making it less stable. And so because it's less stable, it's going to be more reactive. So stability and reactivity are inversely related. Now, the fluorine atom, it's electronegative, so it likes to pull electron density toward itself. So therefore, it neutralizes the carbanion. It makes it more stable and therefore less reactive. So electron withdrawing groups, they stabilize carbanions. Electron donating groups stabilize carbocations, or any electrophile for that matter. In this video, we're going to go over intermolecular forces, IMF. Now, you need to know that ionic interactions are stronger than hydrogen bonds, which are stronger than dipole-dipole interactions, which are stronger than LDF forces. Now, typically, you have an ionic interaction whenever you have a metal combined with a nonmetal. And normally you have hydrogen bonds whenever hydrogen is directly attached to nitrogen, oxygen, or fluorine. Now, dipole-dipole interactions usually exist between polar molecules, and LDF forces are found in everything, but their effect is predominant in nonpolar molecules. Nonpolar molecules only have London dispersion forces, or van der Waals forces. Now, a substance that has hydrogen bonds also has dipole interactions in LDF, and a substance that is polar has dipole interactions and LDF. But if it's nonpolar, it only has LDF. So here's an example of an ionic bond. The interaction between the sodium ion and the chloride ion is an ionic bond. So whenever you have a positively charged ion, it's called a cation, and a negatively charged ion is called an anion. Opposites attract. So sodium feels a force that pulls it towards the chloride ion, and the chloride feels a force that pulls it towards the sodium ion. And so that's an electrostatic force that pulls them together, and that creates the ionic bond. Now let's talk about the hydrogen bonds that are found in water. The oxygen part of water has a partial negative charge. Oxygen is more electronegative than hydrogen, and so it's going to pull the electrons toward itself. And so it develops a partial negative charge. Now, the hydrogen part of water has a partial positive charge. The interaction between the electronegative oxygen of one molecule with the hydrogen of another water molecule, that makes up the hydrogen bond. So the hydrogen bond is an intermolecular bond because it's between two molecules. Whereas the OH bond, this is a polar covalent bond. The reason why it's called a polar covalent bond is because the electrons are shared unequally in that bond. But this is an intramolecular bond, not an intermolecular bond. Intra means that it's inside or within a molecule, but the hydrogen bond exists between molecules. So in organic chemistry, substances that have hydrogen bonds include alcohols, whenever you see an OH group, carboxylic acids, and amines, just to name a few. So these substances typically have relatively high boiling points for molecules due to hydrogen bonding. Now, substances that are polar have dipole-dipole interactions. A hydrogen bond is a special type of dipole-dipole interaction. It's a very strong dipole-dipole interaction. But let's consider formaldehyde. So formaldehyde is a one-carbon aldehyde with two hydrogen atoms. Now the oxygen atom within the formaldehyde has a partial negative charge because it's electronegative and it pulls the electrons toward itself. So the carbon atom is electron deficient. It has a partial positive charge. So the interaction between one formaldehyde molecule with another creates the dipole-dipole interaction. So this partially positive carbon atom on the right is attracted to the partially negative oxygen atom on the left. And so this is the dipole-dipole interaction. So keep in mind, a polarized substance is basically a substance where one side is positive and the other side is negative. Whenever you have an object with a separation of charge, this object is said to be polarized. And it has two poles of charge, so it's called a dipole. One side is positive and the other side is negative. The dipole moment always points towards the negative side. Now, if you have a nonpolar molecule, it only has LDF forces. LDF forces are temporary induced dipole forces. So, let's say if you have an atom, and the atom is neutral, the electrons are distributed evenly, and in the middle, you have the nucleus, which has a positive charge. So this atom is neutral and it's nonpolar because the electrons are distributed evenly. But sometimes the electron cloud could be distorted, and so you might have more electrons on one side than on the other side. So in this case, the left side, which has more electrons, is going to be partially negative, and the right side, which has less electrons, is partially positive. So let's say if you have another atom next to it that is nonpolar, this one right here is polar, or slightly polar, due to the separation of charge. Now this other neutral one, or this other atom that's nonpolar on the right, the electrons in this atom are going to be attracted to this partially positive charge. So therefore, they're going to drift to the left side. So as a result, as they drift towards the left side, you're going to have more electrons on the left and less on the right. So therefore, the left side is going to have a partial negative charge, and the right side is partially positive. So the distortion of the second atom, or this atom on the right, was created by this one. Because of the partial positive charge on the right side, it created a partial negative charge on the left. So we created a temporary induced dipole. The reason why it's temporary is because these electrons can go back to this side, and they can be evenly distributed, become a nonpolar again. So the fact that these temporary dipoles can be created and they can go away, they're very short-lived. But these small interactions, they make up the van der Waals forces, or the London dispersion forces. They're found in every molecule, but nonpolar molecules, this is all they have. So as the molar mass, or as the number of carbon atoms increases, the number of electrons increases. So the likelihood of polarizability, where this nonpolar atom turned into a slightly polar atom, the polarizability will increase as the number of electrons increases. So heavy molecules are more likely to create temporary induced dipole moments than smaller molecules. And so that's why heavier molecules have a higher boiling point. So as the polarizability increases, the overall London dispersion forces will increase for that molecule. So nonpolar substances like alkanes, alkenes, alkynes, the predominant force that is active on these molecules are the London dispersion forces. Anytime you have a compound that contains only carbon and hydrogen, it's nonpolar. The carbon-hydrogen bond is relatively nonpolar. So which substance has the higher boiling point? So between 1-butanol and pentane, which one has the higher boiling point? Now the alcohol has hydrogen bonds, and pentane, which is nonpolar, only has LDF forces. So because hydrogen bonds are stronger than LDF forces, the alcohol has a higher boiling point. So now what about a carboxylic acid versus an alcohol? Which one has a higher boiling point? It turns out it's the carboxylic acid. Now both molecules have hydrogen bonds. They both have the OH, but also the carboxylic acid has the carbonyl group. So the carboxylic acid is more polar. It has two polar regions as opposed to one. And so therefore the carboxylic acid has a higher boiling point. Also, the hydrogen bonds that can be formed in a carboxylic acid is pretty significant. So let's draw two carboxylic acids next to each other. So the hydrogen of one carboxylic acid and the oxygen of the other, it creates like an intramolecular hydrogen bond. Not intramolecular, but like that's the intermolecular hydrogen bond. As you can see, there's two of them, and so that increases the boiling point. Now, which one has a higher boiling point? An alcohol or an amine? It turns out that alcohols have higher boiling points than amines. If you compare the OH bond and the NH bond, hydrogen has an electronegativity value of 2.1, and for nitrogen is 3.0, but oxygen has an EN value of 3.5. So because the electronegativity difference is greater in the OH bond than the NH bond, the OH bond is more polar, and so that hydrogen bond is stronger. Now, what about octane compared to butane? Which one has the higher boiling point? It turns out that it's octane because octane is bigger, and so since it has more carbon atoms, it has a higher molar mass and therefore more electrons. As you increase the electrons, the polarizability goes up, which means that there's more London dispersion forces. And so octane has a higher boiling point than butane. So typically, the structure that has more carbon atoms usually has a higher boiling point. Now, what if the number of carbon atoms are the same? Let's say if we're comparing pentane with neopentane. Which one has the higher boiling point? The one with the higher boiling point is the one, it's the straight chain alkane compared to the branch alkane. The reason why, the straight chain alkane has more surface area, and so there's more, the chances of London dispersion interactions between two molecules greatly increases. Neopentane has less surface area, and so it's going to have a lower boiling point. So whenever you have straight chain alkanes, what they can do is they can stack on each other. And so the intermolecular forces of attraction between these molecules greatly increases due to the stacking. Now, what about a ketone, in this case 2-pentanone, compared to pentane? Which one has a higher boiling point? Now, pentane is an alkane, and so it's nonpolar, but the ketone has the carbonyl group. Whenever you have a carbonyl group, that group is polar. The oxygen is partially negative, and the carbon is partially positive. And so, whenever you have that separation of partial charge, you have a polar functional group. And if it's polar, it has dipole interactions. If it's nonpolar, all it has is LDF forces. And dipole interactions are stronger than LDF forces. Therefore, the ketone has a higher boiling point than a typical alkane. Now, what about octanol compared to butanol or 1-butanol? Which one has a higher boiling point? Now, they both contain hydrogen bonds. However, octanol has more carbons. So even though both compounds contain a polar group and they both have hydrogen bonds, the one that is bigger usually is the one that has a higher boiling point. So 1-octanol is going to have a higher boiling point than 1-butanol. So now let's move on to water solubility. Which of the following compounds is more soluble in water? So if we compare 1-butanol and pentane, which one is more soluble? Now, what you really need to think about here is which one is more polar. Like dissolves like. Water is a polar molecule. So the substance that is more polar is going to have a greater solubility in water. So because butanol has a polar functional group, it's going to be more soluble in water than pentane. Now, what if we were to compare a carboxylic acid and an alcohol? Which one is more polar? So both molecules contain the OH group, but the carboxylic acid also have the carbonyl group. So the carboxylic acid is more polar than the alcohol. So therefore, the carboxylic acid is going to have a higher solubility in water than the alcohol. Now, what if we have a deprotonated carboxylic acid? In this case, a salt, compared to a protonated carboxylic acid. So which one is more soluble in water? So on the right, we have hydrogen bonds, but on the left, we have an ionic compound. Soluble ionic compounds, well, sodium is an alkali metal, and if you know the solubility rules, alkali metals are always soluble in water. Ionic compounds, which have charges, they're extremely soluble in water. So the solubility of butanoate is greater than butanoic acid due to the fact that it's ionic. So if you were to compare the solubility of benzoic acid and sodium benzoate, the solubility of sodium benzoate is significantly greater than benzoic acid. Even though this part is polar, this region here, which contains only carbon-hydrogen bonds, is, well, it has carbon-carbon bonds as well, but it doesn't have any other elements than carbon and hydrogen. This region is nonpolar. So this molecule is like slightly soluble in water, but sodium benzoate is very soluble in water due to the fact that we have ionic bonds. Now, what about 1-butanol versus 1-octanol? Which one has a higher solubility in water? Now, even though octanol has a higher boiling point, it turns out that butanol has a higher solubility. So here's the polar region. They have the same polar region. However, this is the nonpolar tail. This is the part that doesn't like water. And because of this huge nonpolar tail, it's less soluble in water. So alcohols with a lot of carbons are not soluble in water. However, alcohols that only have like 3 or 4 carbon atoms, they're very soluble in water. Methanol, ethanol, extremely soluble. Propanol, butanol, pentanol, they're soluble as well, but after you go past 4 or 5 carbon atoms, the solubility greatly decreases in water. Now, what if we compare 2-pentanone with hexane? Which one has a higher solubility in water? Well, hexane is an alkane and it's completely nonpolar. It doesn't mix with water. However, because of the ketone functional group, that region is polar. So the ketone is slightly polar in water. So this is going to have a higher solubility in water. Now, what if we were to compare a ketone with an alcohol? Which one has a higher solubility in water? So they both contain polar groups, but the alcohol has hydrogen bonds, and so therefore this is going to be more soluble in water. Now the next thing we need to talk about is acid strength. So on a periodic table we have elements like carbon, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Acid strength increases as you go to the right and as you go down. Now the reason why it increases as you go to the right is because the electronegativity increases. Fluorine is more electronegative than oxygen, so HF is more acidic than water. Now as you go down, the reason why it becomes more acidic is not because of electronegativity. Iodine is less electronegative than fluorine. However, iodine is bigger in size than fluorine. So HF is more acidic than water, which is more acidic than NH3, and that's more acidic than methane. The pKa for HF is about 3.2, for water is about 15.7, for NH3, 38, and for typical alkanes is about 50 to 60. As the pKa decreases, the strength of the acid increases. Now, HI is more acidic than HBr, which is more acidic than HCl, and that's more acidic than HF. And the reason for that is due to size. Iodide is significantly bigger than the bromide ion, which is bigger than chloride, which is bigger than fluoride. So, because iodide is so big, it can stabilize the negative charge better. It can spread the negative charge over a larger surface area. And so, the negative charge is less concentrated. In fluoride, the negative charge is spread out over a smaller region, so it's more concentrated. So, bigger atoms, they can stabilize the charge better than smaller atoms or smaller ions. And so, iodide is more stable than fluoride, which means that base strength increases this way. So fluoride is a stronger base than iodide. As the strength of the acid goes up, the strength of the base goes down. So iodide is a weaker base, fluoride is a stronger base. So because HI is a strong acid, iodide is a very, very weak base. And HF is a weak acid, so fluoride is a stronger base. So the stronger the acid, the weaker the conjugate base. Now, going back to this trend, we said that HF is a stronger acid than water, and this is stronger than NH3, and this is stronger than CH4. So the conjugate base of methane is a very powerful base. So this is going to be stronger than NH2, which is stronger than hydroxide, and this is stronger than fluoride. So base strength increases towards the carbon with a negative charge. and acid strength increases towards HF. Now, there's some other things you need to know. Methanol is a stronger acid than water, and water is a stronger acid than ethanol, which is stronger than terbutanol. Methanol has a pKa of 15.5, and for water it's 15.7. For ethanol it's 15.9, and for terbutanol it's 18. Typically, the more carbon atoms an alcohol has, the acidity slightly decreases. As you can see, terbutanol has the most carbon atoms, and so it's the weakest acid out of these four alcohol, well, the three alcohols. So let's say if we have acetic acid versus ethanol, the pKa of this particular carboxylic acid is about 4.7, and for this alcohol it's 15.9. So why is it that a carboxylic acid is much more acidic than a typical alcohol, other than the fact that it's called a carboxylic acid? So what you need to do is you need to draw the conjugate base. So just take off the hydrogen. That is the acidic hydrogen. So this is the acetate ion, and the conjugate base of ethanol is ethoxide. Now, the reason why the carboxylic acid is more acidic than the alcohol is due to something called resonance stabilization of the conjugate base. We can draw a resonance structure for acetate. This lone pair from this oxygen can move here, causing the pi bond of the carbonyl group to break, pushing a lone pair on the other oxygen. And so if we were to draw the resonance structure, it would look like this. So as you can see, the negative charge is spread across two oxygen atoms as opposed to one. So whenever you can spread a negative charge over a larger area, you have a more stable situation. So the fact that two oxygen atoms bears a negative charge means that it's more stable, as opposed to one oxygen atom bearing the negative charge. Here, the electrons on this oxygen atom are localized. The term localized means that they're stuck where they are. They can't really move. Those electrons are stuck on that oxygen atom. However, the electrons in this oxygen atom are not localized. They're delocalized because they can move between two oxygen atoms. So whenever you have lone pairs that are free to move, they're called delocalized electrons. So what you need to know here is that whenever you can draw resonance structures for a conjugate base, the more stable that conjugate base will be, and the acid is going to be a stronger acid. So let's look at another example that illustrates this fact. So let's compare phenol, which is a benzene ring and an alcohol, with cyclohexanol. The pKa of cyclohexanol is about 16, and the pKa of phenol is 10. So why is phenol so much more acidic than cyclohexanol? And how much stronger is phenol compared to cyclohexanol? If the pKa difference is about 1, that means that the acid with the low pKa is 10 times stronger than the other acid. If the difference is 2, the magnitude is 10 squared, which is 100. So here, the difference in pKa is 6. So phenol is 10 to the 6 times stronger than cyclohexanol in terms of its acid strength. So phenol is 1,000,000 times more acidic than cyclohexanol, because 10 to the 6 is 1,000,000. But now let's draw the conjugate base of these two compounds. So Here is the conjugate base for phenol, and below we're going to draw the conjugate base for cyclohexanol. So as you can see, cyclohexanol, the conjugate base, doesn't have any resonance structures. So here we only have localized electrons. The oxygen, it bears the entire negative charge. But in phenol, or the conjugate base of phenol, which is called the phenoxide ion, the oxygen doesn't have to bear the negative charge by itself. The negative charge can move around the ring. This lone pair can form a double bond and push a pair of electrons on that carbon. And so we can draw this resonance structure. Now this lone pair can move here, causing the lone pair to jump 2 carbons away. And so we can get another resonance structure. Whenever you draw resonance structures, you need like this double arrow to show that it's a resonance structure. So now we have this. And then this lone pair can form another double bond, and it could put a negative charge here. So as you can see, the negative charge can be distributed between the oxygen atom and 3 carbon atoms. So therefore, the negative charge in phenoxide is more stable than the conjugate base of cyclohexanol due to resonance stabilization of the conjugate base. And so that's why phenol is much more acidic than cyclohexanol. So here's a question for you. Which one is the stronger acid? A sulfonic acid or a carboxylic acid? So notice that if you were to draw the conjugate base, there's 3 oxygens on the sulfur, and so the negative charge can move between 3 oxygen atoms, but for the carboxylic acid, the negative charge can only move between 2 oxygen atoms. So therefore, sulfonic acid is much more acidic than a carboxylic acid. The pKa of a carboxylic acid is about 4.7 for acetic acid, but for other carboxylic acids it could be like 4 to 5. For this sulfonic acid is around -1. It's in the negative region. So the sulfonic acid is much more acidic than a regular carboxylic acid. So if you were to take this -1 charge and divide it by the 3 oxygens, each oxygen bears a charge of -1/3. For here, for this one, it's -1/2. So the smaller the charge per oxygen atom, the greater the stability. -1/3, well, 1/3 is less than 1/2 if you ignore the negative sign. So if you can share a negative charge among many atoms, it's going to make the conjugate base more stable, therefore the acid will be a stronger acid. So now, if we were to compare ethanol with ethane thiol, which one is more acidic? So keep in mind, acid strength increases as you go to the right and as you go down. So sulfur is below oxygen on a periodic table. So therefore, we should expect that the thiol is more acidic than the alcohol. Now the pKa for most alcohols is about 16. For ethanol, it's like 15.9. For a typical thiol, it's about 10. But for this ethane thiol, it's about 10.6. So as you can see, because sulfur is a bigger atom, thiol is going to be more acidic. So if you draw the conjugate base, here you have oxygen, and here you have a sulfur with a negative charge. But keep in mind that sulfur is bigger than oxygen. So because sulfur is a bigger atom, it has more room to spread out the negative charge, and that's why it's more stable. So whenever the conjugate base is more stable, the acid is stronger. So ethane thiol is a stronger acid. It has a lower pKa value. Now sometimes you might be given a reaction and you need to determine if the reaction will work in the way that is written. So which one is going to act as the acid and which one is going to behave as the base? Well, fluoride can't act as an acid because it doesn't have any hydrogens to give. So it has to act as the base. And this has to be the acid. Now, according to the Bronsted-Lowry definition of acids and bases, acids are proton donors, bases are proton acceptors. So fluoride is going to accept a proton. So we're going to draw an arrow from the fluoride ion to the hydrogen. What that means is that fluoride is going to donate a pair of electrons to form the bond between HF. And these electrons are going to go back to the oxygen. So oxygen currently has 2 lone pairs, but soon it's going to have 3 lone pairs. So this is the methoxide ion on the right side. So because methanol, it lost a hydrogen, it turned into the conjugate base. Whenever you take away a hydrogen from something, you create the conjugate base. And whenever you add a hydrogen to something, you create the conjugate acid. So HF is the conjugate acid and methoxide is the conjugate base. But now, will this reaction work? So you have to look at the pKa's of the acids on both sides. The acid on the left is methanol, which has a pKa of about 15.5. And the acid on the right is hydrofluoric acid, which has a pKa of 3.2. So methanol is a weak acid relative to HF. And HF is a stronger acid than methanol because it has a lower pKa. So the reaction, it shifts in a direction towards the weaker acid, or the side with the higher pKa value. So it's not going to shift to the right, rather it's going to shift to the left. So this reaction, it doesn't work in the way that it's written. Now granted, these reactions are reversible, but the equilibrium favors the reactants because the pKa is higher on the left side. It always goes from the strong acid to the weak acid. A weak acid can't create a strong acid, but a strong acid can create a weaker acid in the course of a reaction. So consider this reaction. So here we have the acetate ion, and we're going to react it with ethanol to produce, well, before we write the products, what do you think the products will be? So acetate has to act as the weak base. So it's going to be the Bronsted-Lowry base. It's going to be the proton acceptor. And ethanol has to act as the weak acid. It's going to be the proton donor. So the acetate ion is going to grab a hydrogen from ethanol. So, and we're going to get acetic acid and the ethoxide ion. So here's the question for you. Does it work in the way that it's written? Does reaction, does it favor the products or does it favor the reactants? In which direction will the reaction shift? Let's say this is reversible. So the acid on the right is the carboxylic acid. That's the conjugate acid. Because whenever you add a hydrogen to something, it turns into the conjugate acid. Here we remove the hydrogen from ethanol, So this is the conjugate base. Now the pKa of ethanol is 15.9, and for acetic acid is about 4.7. So the left side has the weaker acid. The carboxylic acid is a stronger acid relative to ethanol. So it's going to go towards the side of the weak acid, which is the left side. So this reaction is reactant favored as well. Now let's talk about alkynes, alkenes, and alkanes. The pKa of an alkyne is about 25. For this particular alkene is about 44, and for most alkanes it's about 50 to 60. So why is it that the alkyne is much more acidic than an alkane? And it has to do with the hybridization. What's the hybridization of this carbon atom? Because there's two groups that it's attached to, it's going to be sp hybridized. So if you have one s orbital and one p orbital mixed together, it's 50% s and 50% p. Now, what's the hybridization of this carbon atom? So it has three groups. So it's going to be s1p2 hybridized, or sp2 hybridized. So out of three orbitals, there's one s, 2p. So 1/3, there's one s out of three orbitals. 1/3 is 33%. So this has 33% s character. And for ethane, the hybridization of that carbon, it has four groups, so it's going to be s1p3 hybridized. So for sp3 hybridization, you have one s orbital out of a total of four orbitals. So 1 out of 4, that means that we have 25% s character. So the reason why the alkyne is much more acidic than alkenes and alkanes is because it has more s character. So now let's talk about Newman projections. Let's draw the Newman projection for butane. So butane has 4 carbons, and it's CH3, CH2, CH2, CH3. Now let's draw the Newman projection along the C2, C3 bond. So that's along these two carbon atoms. So let's draw those two carbon atoms first. Now, carbon 2 has a methyl group, and it has these two hydrogens attached to it. Carbon 3 also has a methyl group, and it has two hydrogens attached to it. So now let's draw the Newman projection. So what we're going to do is we're going to draw a circle, and this dot in the center represents the second carbon, the C2 carbon. So the C2 carbon has 3 groups, not including the C3 carbon. It has the methyl group, the hydrogen, and another hydrogen. So we're going to put a CH3, and 2 hydrogens. Now the C3 carbon is in the back, and in the Newman projection it's difficult to see. You can't see it, it's behind it. But that C3 carbon has 2 hydrogens and a methyl group as well. So here's the methyl group and the 2 hydrogens. And so that's how you can draw a Newman projection. Now this is one of the different ways that we can draw it. There are other Newman projections that we can draw as well. Let's rotate the back carbon. So I can put the methyl group on this side, and the other two hydrogens here. Or I can also draw it a different way. I can put the other methyl group right behind this one, and so the hydrogens will be here. And there's another way you can draw this as well. Now I can put one of the methyl groups, or the other methyl group, with a hydrogen. So these are the four different ways we can draw the conformations of butane. So as you can see, the butane molecule, it can rotate. And so the methyl groups, they can be close to each other or they can be far apart. So here the dihedral angle is 60 degrees. The methyls are 60 degrees apart from each other. And in this structure, the dihedral angle is 180. As you can see, they're as far apart as possible. And here the dihedral angle is 0, and between the two methyl groups here it's about 120. Now you need to know the names that corresponds to these conformations. So whenever the methyl groups are completely far apart as possible, this is the anti-conformation. It's also staggered. There's two staggereds: the anti-conformation and the Gauche conformation. Now, whenever they're very close to each other, it's eclipsed. So this one here is the Eclipse conformation, and this one, where the two methyl groups are directly attached to each other, this is totally eclipsed. So think of when the moon eclipsed the sun. You can't really see the sun behind the moon. So in this case, the red methyl eclipsed the blue methyl, meaning you can see the red methyl, but you can't see the blue methyl because the blue one is directly behind the red one. And so that's what it means when it's eclipsed. So the other two, anti and Gauche, these are two different forms of staggered conformations. So which one is more stable, a staggered conformation or an eclipse conformation? When it's eclipsed, you have something called torsional strain. As butane rotates, it's difficult for the hydrogen atoms to approach next to each other. And so as they approach, that resistance to twisting is called torsional strain. The atoms, they don't want to be eclipsed with each other. And so that resistance to twist to that eclipse state, that's torsional strain. So anytime you have an eclipse conformation, you have torsional strain. Now there's another strain that's also present. Whenever the methyl groups are next to each other, because they're so bulky, as they approach each other, their electron clouds repel each other. And so you have a strong electron repulsion. And as a result, you have something called steric strain or steric hindrance. So it turns out that the most stable structure is the anti-conformation because the methyl groups are as far apart as possible. In the eclipse conformation, here you have a torsional strain and you have a small amount of steric strain. Here you have a large amount of steric strain because the two bulky methyl groups are clashing. And in the Gauche conformation, you have a small amount of steric strain. It's still there, but it's less than the totally eclipsed conformation. So what you need to know is that the anti-conformation is the most stable. So I'm going to put number 1 for the most stable. The Gauche conformation is the second most stable, and then it's the eclipse. The totally eclipsed conformation is the least stable, because not only do you have torsional strain due to the fact that it's eclipsed, but you also have steric strain because the bulky methyl groups are clashing with each other. Now let's draw an energy diagram for butane. On the y-axis, we're going to plot the potential energy of the molecule, and on the x-axis is going to be the dihedral angle. So the graph is going to look something like this. So as the energy increases, whenever you increase the potential energy of a molecule, the stability decreases. So something that has a lot of potential energy is less stable. So therefore, we know that the totally eclipsed structure is the least stable. So at the highest, we have the totally eclipsed conformation. Now at the second highest peak are the eclipse conformation. And the lowest energy is going to be anti. And the second lowest is the Gauche conformation. So totally eclipsed, the angle between the two methyl groups is about 0 because they're right next to each other. We said Gauche was 60, Eclipse was 120, and anti is 180. Now if you count it the other way, Eclipse is also 240 because 120 and 240 adds up to 360. So if you start at this point and if you go 120 this way, it's the same as going 240 in the opposite direction. So 120 and 240, basically they're the same conformation. They're both eclipsed. And 300 is Gauche because if you go 60 to the left, it's the same as going 300 to the right. 300 plus 60 is 360. And 360 is also totally eclipsed. 0 means you haven't moved anywhere, but if you travel 360, that's a complete revolution. You're going to end up where you started. So you need to know what structure corresponds to which portions, or to the portions of the graph that you see. So at the very top, it's always going to be the totally eclipsed structure because it's the least stable. And the second highest is the eclipsed structure, and the lowest is the anti, and the second lowest is the Gauche structure. So at the bottom, you have the staggered conformations, which include Gauche and anti, and at the top, you have the eclipse conformation. The next important molecule that we need to talk about is cyclohexane. Now there's different ways you can draw cyclohexane. One way that we drew earlier was basically a hexagon ring. Now cyclohexane has different forms. It has different conformations. So it can rotate and it can bend and create different shapes. There's 4 conformations that you need to be aware about. You need to know the stability. The chair conformation is more stable than the twist bolt conformation, and the twist bolt conformation is more stable than the bolt, which is more stable than the half chair. Now we're going to focus more on the chair conformation because cyclohexane is usually in that form, but make sure you know the stability. So the chair conformation is the most stable form of cyclohexane. So let's go ahead and draw the chair conformation, or at least one way of drawing it. So this is the axial position. This is axial up, axial down, axial up, axial down, axial up, axial down. So they alternate. So the axial position is always up and down. And then you have the equatorial position. So if axial is up, then the equatorial has to be slightly down. This is equatorial up, equatorial down, equatorial up, equatorial down, equatorial up. So on a carbon, you have one group that's up and the other that's down. And so make sure you know the difference between an axial bond and an equatorial bond. Now sometimes you might get a question to ask you, draw the most stable conformation, or the most stable chair conformation of 1-terbutyl 4-methyl cyclohexane. So how would you do that? So let's draw 4 chair conformations. Now, I'm going to put the tert butyl group on the first carbon. And so the methyl has to be on carbon 4. So this is 1, 2, 3, 4. So that's 1 tert butyl 4 methyl cyclohexane. Now let's say if I keep the tert butyl group at the top or in the axial position. To get a different conformation, I can put the methyl in the equatorial up position. Or if I put the tert butyl in the equatorial down position, I can keep the methyl in the axial position, or I can put it in the equatorial position. So this is the 4 different forms of 1 tert butyl 4 methyl cyclohexane. Now you need to know which forms are cis and which ones are trans. So which one do you think is cis and which one do you think is trans? So here, this is in the axial up position, this is in the axial down position. Whenever it's up and down, it's going to be trans. So for this one, this is up, and this is up as well. So that's going to be the cis isomer. This is down, that's facing down. So if they're going in the same direction, it's going to be cis. And for the last one, this is going down, but this is going up. So this is the trans isomer. So now, which of these is the most stable structure? Is it better to put a group in the axial position or in the equatorial position? It's more stable if you can put a bulky group in the equatorial position. The reason why is you can reduce 1,3 diaxial strain. So there's a hydrogen here and there's another hydrogen here. So notice that each hydrogen is 1,3 apart from the tert butyl group, if you count it that way or if you count it this way. And so because they're parallel to each other, you're going to have 1,3 diaxial strain, which is indicated by those blue lines. And so the axial position is less stable than the equatorial position. So because for the first compound, both groups are in the axial position, this is going to be the least stable conformation. So we're going to say this is number 4 for least stable. Now, number 1, the most stable one, is where they're both in the equatorial position, which is this one. So this is the most stable conformation. Now, the remaining 2, the one that's more stable is the one where the bulkier group is in the equatorial position. You want to put the bulkier group, which is the tert butyl group, in the equatorial position because it's going to have less strain compared to the smaller, less bulkier group. So this is going to be number 2 because the bulky group is on the equatorial position. This is number 3 because the bulky group is in the axial position. It's better to put the bulkier group in the equatorial position than the methyl group in the equatorial position if you have to choose one over the other. So sometimes you might get a question to ask you which is the most stable conformation for, let's say, cis 1-tert butyl 4-methyl cyclohexane. So you're comparing only these two because these are the cis isomers. Therefore, this one is going to be more stable because the bulkier group is in the equatorial position. Now, if the question asks you which one is, draw the most stable conformation or chair conformation of trans 1-tert butyl 4-methyl cyclohexane, you're only looking at these two. And the most stable one out of those two is this one. So that's why you need to know which one is cis and which one is trans. So what we've considered so far can be termed conformational isomers. So if you hear that term, think of like Gauche, anti, Eclipse. Those are conformational isomers of butane. And if you think of the words like chair conformation, half chair, twist boat, those are conformational isomers of cyclohexane. But what about constitutional isomers? What are constitutional isomers? Well, you need to know what an isomer is. An isomer is basically two molecules where they have the same chemical formula but different structure. A constitutional isomer is one where you have the same chemical formula but a different connectivity. So, for example, the constitutional isomer of butane is this thing, 2-methylpropane. Notice that we have the same number of carbon atoms and the same number of hydrogen atoms. So this is CH3, CH2, CH2, CH3. And here we have a CH in the middle with 3 CH3s around it. So in both compounds, we have 4 carbon atoms, 10 hydrogen atoms, but a different structure. So these are called constitutional isomers. Same structure, but different connectivity. So how can we draw all of the constitutional isomers for pentane? So what you need to do is draw 4 carbons and put a methyl group somewhere. So that's one isomer. Another way you can do it is by drawing 3 carbons and putting 2 methyl groups here. So as you can see, we have 5 carbons in total, but we have different structures. Now, how many constitutional isomers can we draw for hexane? So let's go down to 5 carbons. We could put a methyl on carbon 2, or we can put a methyl on carbon 3. As you can see, the names of these constitutional isomers are different. This is called 2-methylpentane, and the other one on the right is 3-methylpentane. Now what we can't do, we can't put a methyl group on carbon 4, because that's not really carbon 4. You would count it this way. It would end up being carbon 2, so it would be 2-methylpentane. So we can only put a carbon atom on carbon 2 and 3, and we'll get different structures. Here's a general rule. If the name is different, then you've drawn a correct constitutional isomer. If you get the same name, it's not a constitutional isomer. So as you mentioned, this one is called 3-methylpentane. Now, are there any other constitutional isomers that we can draw? Well, we can go down to 4 carbons, and we can put a methyl on carbon 2 and carbon 3, or we can put 2 methyls on carbon 2. Either case, we still have a total of 6 carbons. And that's as far as we can go with hexane. So for the sake of practice, let's try one more example. Let's draw all the constitutional isomers for heptane. So let's go down to 6 carbons. We can put a methyl on carbon 1. We can put it on carbon 2, and this is carbon 3. Now, for hexane, here's the line of symmetry. If you put the methyl group on carbon 1, it becomes heptane. If you put it here, it's the same as putting it here. Both cases, it's going to be 2-methylhexane. And if you put it here, that's 3-methylhexane. And if you put it here, that's also 3-methylhexane. So right now we have a total of 3 constitutional isomers. So now let's go down to 5 carbons. To get a total of 7, we need to add 2 methyl groups. We can add one on carbon 1 and another one, on carbon 2 and carbon 3. We can put 2 methyls on carbon 2. We can put 2 methyls on carbon 3. We can put, a methyl on carbon 2 and 4. And I think that's about it for the 5 carbon chain. So now we can go down to a 4 carbon chain, and we can put 2 methyls on carbon 2 and a methyl on carbon 3. And I believe that's about it for heptane. That's the most or the maximum amount of constitutional isomers that we can draw for heptane. So now let's talk about cis-trans isomers. Also known as geometric isomers. So which of these 2 isomers is the cis isomer and which one is the trans? So on the left, we have the trans isomer, and on the right, we have the cis isomer. So the cis isomer has the methyl groups on the same side, whereas the trans isomer has the methyl groups on opposite sides. The trans isomer is usually the E isomer, and the cis is usually the Z isomer. Now, which of these two alkenes is more stable? Typically, the trans isomer is more stable. As you can see, the methyl groups are further away from each other. When they're closer, it's going to be less stable due to steric factors. Now, keep in mind, cis-trans isomers are also known as diastereomers. We'll talk about diastereomers later throughout the course of this video. Now, consider these two molecules. Which one has the greater dipole moment? Is it the cis isomer or the trans isomer? The one with the greater dipole moment is the one that's more polar. The carbon-fluorine bond is polar. For the trans isomer, to draw the dipole moment, you need to draw the arrow facing towards the more electronegative element. Notice that these arrows, they cancel because they point in opposite directions. So therefore, this is nonpolar, and the dipole moment is equal to 0. Now, for the cis isomer, notice that these arrows, they don't cancel. So we have a net dipole moment. It's greater than 0. It's positive, and so therefore, this molecule is relatively polar. So that's how you can tell which molecule has the greater dipole moment. You need to draw the dipole moments and see if they cancel or not. Now consider this molecule. How would you name it? This is a bicyclic compound. And the first thing that you need to do is to identify the bridge-headed carbons. The bridge-headed carbons are these carbons. And you need to know how many carbons are in each link. So in this link, how many carbons are there? So notice that there's 2 carbons. So we have 2 on this side. And what about on this side? So notice that there's 2 carbon atoms on this side. And what about this side? Notice that there's only 1 carbon atom. So the total number of carbon atoms that we have in this structure is 7. So to name it, it's going to be bicyclo, and in descendant order, it's going to be 2, 2, 1, and then 2 plus 2 plus 1, and then add the 2 bridgehead carbons, that's going to be 7, so heptane. That's how you can name a bicyclic compound. So let's work on a few examples. Go ahead and name this one. So here are the bridgehead carbons. We have 2 carbons on the left side, 1, 2. And on the right side, there are 3 carbons. And in the top link, we only have 1. So it's going to be bicyclo, and in descendant order, 3, 2, 1, and then 3 plus 2 plus 1 is 6, add 2 to it. We have a total of 8 carbons. So 3, 2, 1 octane. So what if we have a ring, well, a bicyclic compound that looks like this? How would you name it? So here are the bridgehead carbons. They are the tertiary carbons. And notice that on the left side, we have 1, 2, 3, 4 carbon atoms. And on the right side, we have 1, 2, so 2 carbon atoms. And in this link, there's no carbon atoms. There's no carbon atoms in that link between those bridgehead carbons. So to name it, it's going to be bicyclo, in descendant order 4, 2, 0. 4 plus 2 plus 0 plus the 2 bridgehead carbons. That means we have a total of 8 carbons, so this is going to be octane. So that's how you can name bicyclic compounds. Now let's spend some more time talking about resonance structures. We talked about it before, but let's go into more detail. To draw a resonance structure, you can't move any atoms. You're only allowed to move electrons. So typically, the arrow, the electrons, it flows from a region of high electron density to a region of low electron density. Think of water. Water flows from a high position to a low position, and the electrons, they follow the same pattern. They're going to flow towards the positive charge, which is a region of low electron density. So the double bond is like the nucleophile. It's the region of high electron density. The plus charge is like the electrophile. It's the region of low electron density. So the arrow is going to flow towards the positive charge. So this double bond, the 2 electrons in that pi bond is going to move towards the carbocation. And the plus charge is going to move 2 carbons towards where the double bond was. So it's going to jump 2 carbons to the left. And we need to use this double arrow to represent that we're drawing resonance structures. And so the double bond is here, and the plus charge is now here. So try this example. Go ahead and draw as many possible resonance structures for this particular ion. By the way, whenever a plus charge is 1 carbon away from a double bond, it's called an allylic cation. Allylic carbocations are more stable than regular carbocations due to resonance stabilization. So this double bond can move here, and the plus charge is going to jump 2 carbons towards the double bond. And so we have this structure, and this double bond can also move here. So we can draw 3 resonance structures. So the plus charge is shared among 3 carbon atoms. Try this one. So the double bond can move towards the carbocation, and so we can draw the first resonance structure, which is going to look like this. And the plus charge is going to move 2 carbons towards the double bond that move toward it. So the plus charge and the double bond, they're going to trade places. And so now this double bond is going to move towards the plus charge, and those 2 are going to trade places. And so now the plus charge is over here, and this double bond can move towards it. And so now there we have the plus charge. So that's how you can draw the resonance structure for that particular cation. Now what if we have a negative charge? How is it different now? So which is more nucleophilic, the double bond or the carbanion? The carbanion is more nucleophilic than the double bond. So the arrow is the electrons are going to flow from the negative charge towards the double bond. It's going to flow from a region of high electron density to a region of low electron density. And so now the double bond is here, and we have a negative charge. So we need 2 arrows for this example as opposed to 1. So try this example. So this oxygen can use a lone pair, and it's going to form a double bond, pushing a lone pair over here. And so this carbon now has a negative charge. And then this lone pair can be used to form a pi bond, pushing the negative charge on that carbon. And so now we have this structure. Try this example. So whenever you have a carbonyl group is electrophilic. The oxygen can pull electrons toward itself. And so the carbon of the carbonyl group has a positive formal charge. And whenever a carbon atom has a positive charge, it's electrophilic. If the carbon atom has a negative charge, it's nucleophilic. So nitrogen, which is electron rich, it can donate a lone pair to satisfy the electron poor carbon. And so this oxygen is going to pull the electrons toward itself. And so we're going to get this resonance structure. So now the oxygen is going to have a negative formal charge. And the nitrogen now has a positive formal charge. Whenever nitrogen has 4 bonds, it has a plus charge. And wait, I think I put too many bonds here. This should be a single bond. And whenever oxygen has 1 bond, it has a negative charge. Keep in mind, if you need to calculate the formal charge, it's the valence electrons minus the bonds and the dots. So in the case of nitrogen, which has 5 valence electrons, in this structure it has 4 bonds, no dots, so it has a formal charge of +1. Now, let's say if you have an ester. How would you draw the resonance structure of an ester? So like an amide, the oxygen, which has a lone pair, can push electrons towards the carbonyl group. And so we're going to get this structure. So now the oxygen with the single bond has a negative charge, and the oxygen with 3 bonds is going to have a positive formal charge. Now, which of these structures is more stable? Which one is the major resonance contributor? The major resonance contributor is the one that's more stable, and the one that's more stable is the one that's neutral, which is this one. Whenever you have separation of charge, like the structure on the right side, it's going to be less stable. This is the more reactive form of the ester. Now, the resonance hybrid, the true molecule, lies somewhere in between these two structures. So the ester doesn't exactly look like this, nor does it exactly look like that. It's somewhere in between. However, the ester is going to look more like one of the compounds than the other. Even though it's between, it's going to be shifted towards one side than the other. So the actual ester, the actual molecule, does it look more like this one or like this one? It's going to look more like the molecule that is more stable. So because the structure on the left is the major resonance contributor, the true resonance hybrid, or the true molecule, looks more like this than it does like that. It's between the two molecules, but it looks more like the molecule on the left. So a resonance structure is simply another way in which you can draw a molecule. Now, going back to this structure that we had in the beginning, and where we drew another resonance form, which one of these two structures, actually I just drew the same thing. Let me put the double bond here. So which of these two allylic carbocations is the major resonance contributor, or which one is more stable? So in both cases we have a double bond and a plus charge, so there's no separation of charge. But keep in mind that tertiary carbocations are more stable than secondary carbocations, and secondary carbocations are more stable than primary. This carbocation is secondary because the carbon is attached to two other carbon atoms. And on the right, we have a primary carbocation because the carbon with the plus charge is only attached to one other carbon atom. Since secondary carbocations are more stable than primary carbocations, the structure on the left is the major resonance contributor. So what about these two carbanions? Which one is more stable? So on the left we have a secondary carbanion, and on the right we have a primary carbanion. Now for carbanions, the stability is opposite to that of carbocations. Primary carbanions are more stable than secondary carbanions. So therefore the structure on the right is the major resonance contributor because it's more stable. Now let's go back to resonance structures and draw them. Draw the resonance structure for this molecule. So this oxygen is an electron donating group. Electron donating groups, they can put negative charges on carbon atoms. So this oxygen is going to donate a pair of lone pairs, or a pair of electrons, by means of the resonance effect, and it's going to put a negative charge on this carbon. Electron donating groups are also called electron releasing groups. They release electrons to the molecule. And so now the oxygen is going to bear a positive charge. So this is going to be the major resonance contributor because it's neutral. On the right side we have separation of charge. Here this is positive, this is negative, so that's the more reactive form, the less stable form. So now what's going to happen if we have an electron withdrawn group? Let's say like an aldehyde. Anytime you have a carbonyl group or like a nitro group, those are electron withdrawn groups. So the other oxygen in the other example, it donated electrons to the double bond. The arrow flowed towards the double bond. In this case, the arrow is going to flow towards the carbonyl group. The carbonyl group is going to pull the electrons toward itself. And so that makes it an electron withdrawn group. Electron withdrawn groups, they put positive charges on the carbon atoms. So this carbon atom now has a positive charge. Now, what is the difference between a homolytic cleavage and a heterolytic cleavage? So, in the homolytic cleavage, when the bond breaks, the electrons in the bond are distributed evenly. So the electrons in this bond, there's two of them. And whenever you have two similar elements, or elements with the same electronegativity, when a bond breaks, both atoms are going to gain an electron. We need to use a half arrow to represent the flow of one electron. A full arrow represents the flow of two electrons. So the bromine on the left is going to get one electron, and the bromine on the right is going to get an electron. So this is called a homolytic cleavage, because when the bond breaks, it breaks evenly. The two electrons are evenly distributed among those two bromine atoms. And typically, you're going to get two radicals. Whenever you have two radicals on the right side of a reaction, this represents an initiation reaction. It's an initiation step in a radical reaction. So homolytic cleavages create radicals. Now there's another type of cleavage called heterolytic cleavage, also known as ionic cleavage, because it creates ions. So let's consider the carbon-bromine bond. So this bond is a polar covalent bond because the electronegativity between carbon and bromine are not the same. Bromine is more electronegative than carbon, and so bromine, it pulls the electrons toward itself. And so bromine has a partial negative charge, carbon has a partial positive charge. So when a bond breaks, because bromine is more electronegative, it's going to take away both electrons with it. So therefore, the carbon atom, because it lost electrons, is going to have a positive charge. And bromine, because it gained electrons, it's going to have a negative charge. So heterolytic cleavages, they create ions. So here we have an ion pair. Now what's going to happen if we put an atom that's less electronegative than a carbon? Hydrogen has an electronegativity value of 2.1. For carbon, the EN value is 2.5. For bromine, the electronegativity value was 2.8. So because carbon is more electronegative than hydrogen, it's going to pull the electrons toward itself when a bond breaks. And so the carbon is going to have a negative charge. It's going to be a carbanion. And the hydrogen is simply H+. But typically a base would take away the hydrogen. So the hydrogen is probably going to be attached to a base or something. So anytime you have an atom that's less electronegative than carbon, when that bond breaks, you're going to get a carbanion. If carbon is attached to an element that's more electronegative than itself, when that bond breaks, you get a carbocation. Now you need to be familiar with the 3 steps called initiation, propagation, and termination for radical reactions. So what I'm going to do is I'm going to write a few reactions on the board, and in the meanwhile, determine if it's initiation, propagation, or termination. So here's a quick way to tell. If you have 2 radicals on the right side, it's initiation. If you have 2 radicals on the left side, it's termination. If you have 1 radical on the left and 1 radical on the right, it's propagation. So the first one is initiation because we have 2 radicals on the right side. The second one is propagation. We have 1 radical on each side. The third one is initiation. The fourth one is termination because we have 2 radicals on the left side. The fifth is propagation, and the last one is termination. So that's how you can quickly tell if a step is initiation, propagation, or termination. So now we need to talk about energy diagrams. You need to be able to look at an energy diagram and see if it's endothermic or if it's exothermic. So on the left, we have the reactants and the products, and at the top we have the transition state, also known as the activated complex. The y-axis is the potential energy, and the x-axis is the reaction coordinate. So here we also have reactants, products, and the transition state. Now, the difference in potential energy between the products and the reactants, what is that called? So what is the value that corresponds over here? This is the enthalpy. The enthalpy of the reaction is basically the products minus the reactants. In general chemistry, you've learned it as the sum of the products minus the sum of the reactants. So as you go from left to right, notice the enthalpy change is positive, because as you go from the reactants to the products, the potential energy increases. So whenever delta H is positive, you have an endothermic reaction. Because the products are higher in energy than the reactants, the products, they gain energy, they absorbed it. And so it's endothermic. Whenever you absorb heat energy, it's endothermic. Now, as you go from reactants to products, you have to go down. And so therefore, delta H is negative. Because the products are lower in energy than the reactants, energy was released. And whenever heat energy is released, it's an exothermic reaction. Now, what is the activation energy in this reaction? The activation energy is the difference between the energy of the transition state and the energy of the reactants. This is called the forward activation energy. The reverse activation energy is the difference between the transition state and the products. Now, most of the time, if you hear the word activation energy, and if it doesn't state reverse or forward, it's always assumed to be the forward activation energy, unless specified otherwise. By the way, the video that you're currently watching is the 3-hour trailer version of a longer 9-hour video. So I'm going to post a link to the remaining part of this video, and you can check it out when you get a chance. And let's get back into the lesson. While we're on the subject, the next thing we need to talk about is the Hammond postulate. So basically, the Hammond postulate carries the idea that the transition state resembles more like the species that is closer in energy to it. So for an endothermic reaction, does the transition state resemble more like the reactants or the products? Because the transition state is closer to the products than the reactants for an endothermic reaction, the transition state is going to resemble more like the products than the reactants for an endothermic reaction, based on the Hammond postulate. Now, for an exothermic reaction, it's different. The reactants are closer to the activated complex, so therefore the transition state looks more like the reactants than it does compared to the products. And so that's the main idea behind Hammond's postulate. Basically, the species that is closer in energy to the transition state resembles or looks more like the transition state. Now, the next thing we need to talk about is a catalyst and chemical kinetics. In chemical kinetics, the rate of a reaction is dependent on the rate constant K and the concentration of the reactants. The rate of the forward reaction doesn't depend on the concentration of the products, only the reaction. So let's say if we have a reaction, A plus B turns into C. And let's say if we have the rate law expression, rate equals K times A times B to the second power. And let's throw in D as well. But notice that D is not included in the rate law expression. This whole thing is called the rate law expression. This is the rate of the reaction, and K is the rate constant. So make sure you know the difference between the three terms. Whenever you increase the concentration of the reactant, the rate is going to increase. So the order is basically the exponents. Notice that the exponent of A is 1, so it's first order with respect to A. And for B, the exponent is 2, so it's second order with respect to B. But the overall order of the reaction is the sum of those exponents, 1 plus 2 equals 3. So it's third order overall. Now, because A is first order, if you double the concentration of A, the rate is going to double. If you triple the concentration of A, the rate is going to triple. Now for B, it's squared. If you double the concentration of B, 2 squared is 4. The rate is going to quadruple. If you triple the concentration of B, 3 squared is 9. The rate is going to increase by a factor of 9. So whenever you increase the concentration of a reaction, the rate of the reaction is going to increase. Now, if you increase the temperature of the reaction, the rate constant K goes up, and K is proportional to the rate. So whenever the rate constant goes up, the rate of the reaction goes up. So anytime you raise the temperature, the reaction speeds up. Now, what happens if you add a catalyst? When you add a catalyst to the system, we know that the reaction is going to speed up. By adding the catalyst, the activation energy decreases. And whenever the activation energy decreases, the rate constant K goes up, and the rate of the reaction will go up as well. So consider the following energy diagram. So this is going to be an uncatalyzed reaction. And in yellow, I'm going to draw the catalyzed reaction. So without a catalyst, the activation energy is pretty high. However, when you add a catalyst to the system, the activation energy decreases. A catalyst lowers the activation energy, and that's how it speeds up a reaction. It provides an alternate pathway for the reaction, making it easier. So the only way to get up this hill is to increase the temperature or increase the reactants. And so that's going to speed up the reaction. The greater the hill, the slower the reaction. It's very hard to drive up a mountain, but it's easy to drive up this hill. So when you add a catalyst, it speeds up the reaction by lowering the activation energy. So this is a one-step reaction, by the way. Whenever you have one transition state, you have a one-step reaction. A two-step reaction looks like this. There's going to be two energy maxima. So there's the first transition state, and then here's the second. And so here we have the reactants, the products, and in the middle is something called the intermediate. This is the first transition state, and here's the second. So overall, we can see that this is an exothermic reaction because the products are lower in energy than the reactants. But the first step is endothermic because the intermediate is higher than the reactant. So delta H is positive for the first step, but for the second step, it's exothermic. Delta H is negative. But overall, going from reactants to products, we see that we're going down, so it's exothermic overall. Now, which step is the slow step? Which step is the rate determinant step? Notice that the first transition state is higher in energy than the second. So that means that the first step is the slow step or the rate determinant step. The second step is the fast step. So now let's go over the chlorination, the monochlorination of propane. So typically, to get this radical reaction started, you need to irradiate the sample with light or UV light, or you could heat it as well. Now, this reaction is a radical substitution reaction. It's a substitution reaction because you're going to replace or substitute a hydrogen with a chlorine. And because we're only replacing one hydrogen with one chlorine, it's a monochlorinated reaction. If it was a dichlorinated reaction, we would replace, let's say, two hydrogen atoms with two chlorine atoms. So that's a dichlorinated product. Now, chlorine is very reactive, and as a result, this reaction is non-selective. So the chlorine atom can replace the secondary hydrogen. It can also replace a primary hydrogen. And so you're going to get a mixture of products. Now, for the bromination of propane, it's different. Bromine is less reactive than chlorine. With bromine, you may need to irradiate the sample with light, and you may have to heat it up as well, maybe above 100 degrees Celsius or something. Because this reaction is slow, you have to heat it up. In this reaction, bromine is selective. It's going to go for the secondary hydrogen. And more than 95% of your product is going to be in this form. So this is the major product. So you don't really get a mixture of products. I mean, you do, but the amount of the 1-bromopropane that you will get is insignificant. So for the most part, you get this product. Now you need to be aware of the energy diagrams for these two reactions. So for the chlorination reaction, it's highly exothermic. So the energy diagram looks like this. Notice that the reactants are very high in energy. The reason for that is because chlorine, it's a very reactive radical. And notice that the activation energy is small. Because it has a small activation energy, this reaction is fast. Now, for the bromination of propane, the energy diagram looks different. It looks more like this. And so here you have the reactants and here you have the products. So it's an endothermic reaction. And because the activation energy is so big, this reaction is slow. And so to get it going, you need to add heat and you need to irradiate the sample with light. So you got to put in a lot of energy to get this reaction going. So just keep in mind that bromine, it reacts selectively. It goes for the most substituted hydrogen. And chlorine, it's reactive, it reacts fast, and it's non-selective. It can abstract any hydrogen that comes in contact with it. So, let's say if we have this alkane. Draw the significant products that form in the reaction between chlorine and this alkane. So chlorine is going to replace every hydrogen on this compound. So it can replace the primary hydrogen, the secondary hydrogen, the tertiary ones, and these primary hydrogens are identical to each other. So we don't have to put a chlorine on each of them because they lead to the same product. So we can get 4 different monochlorinated products, not including stereochemistry. So we can get these 4. Now, if you want to include stereochemistry, this product, the Cl can be in the front or it can be in the back. So we can get 2 stereoisomers because this carbon is chiral. It has 4 different groups. It has the methyl group on the right, the chlorine, the hydrogen, and this group on the left. Now, this carbon is not chiral because the methyl groups are identical. For a carbon to be chiral, it has to have 4 different groups. This carbon is not chiral because it has 2 hydrogens. The same is true for this one. Primary carbons are not chiral. Now, what if we take the same alkane and react it with bromine in the presence of light and heat? What's going to happen? So because bromine is selective, it's going to go for the most substituted hydrogen. So 99% of the product could be this product alone, and it's not chiral, so we only get 1 significant product. So let's move away from radical reactions, and let's talk about some other stuff. Let's say if you add heat to a very long alkane. This alkane can break up into 2 smaller alkanes. So we have a total of 9 carbons. So it can break up into 2 small alkanes. And one of them is going to have a double bond. Now, if you heat a long chain alkane with hydrogen gas, it can break up, but you're going to get 2 alkanes instead of an alkane and an alkene. So this is simply called cracking, and this is called hydrocracking. Cracking is the process of heating an alkane and breaking it into smaller alkanes and alkenes. Hydrocracking is doing the same thing. You're heating it. You're going to break it up into 2 smaller alkanes, but you're adding hydrogen gas as well. Now, typically, you might need a catalyst to make this work, to speed it up. By the way, make sure you know that alkanes are known as paraffins. Alkanes are saturated. Alkenes are unsaturated. Alkenes are known as olefins. So now, what is the difference between stereoisomers and constitutional isomers? So, constitutional isomers, they have the same chemical formula, but they're connected differently. So an example of a constitutional isomer is butane and 2-methylpropane. So the chemical formula is the same, it's C4H10. But notice that the connectivity is different. Here we have a carbon atom that's attached to 3 other carbon atoms. In this structure, there's no carbon atom that has 3 other carbon atoms. We don't have any tertiary carbons. We have secondary and primary carbons, but none are tertiary. And so constitutional isomers are connected differently. Stereoisomers, they're connected the same, but the way that they are arranged in space is different. So stereoisomers have the same connectivity, but they differ in their spatial arrangement. So let me give an example. Consider the cis-trans geometric diastereomers. So here we have the cis isomer, and let's draw the trans isomer. Since trans isomers are always known as diastereomers. So notice that this carbon has the exact same connectivity as this carbon. Both carbons contain a hydrogen atom, they're both connected to a methyl group, and they're both connected to a carbon atom that has a CH3 and an H. So the connectivity is the same, but the spatial arrangement is different. Here the methyl groups are close to each other, but here the methyls are far apart. So stereoisomers, they're connected the same, but they're arranged in space differently. Constitutional isomers, they're simply connected differently. So you have a lot of types of stereoisomers. There's a lot of different types. You have enantiomers, diastereomers, epimers, just to name a few. Now let's say if you have pentane, you need to be able to determine if the molecule as a whole, if it's chiral or achiral, and if it has any carbon atoms that are chiral or achiral. So there's no carbon atoms that have 4 different groups, so this molecule is achiral. It doesn't have any chiral carbon atoms. Now, what about this molecule? Does it have chiral carbons? This carbon here with the Br is chiral. We have a methyl group on the right, we have the propyl group on the left, we have a bromine, and we have a hydrogen. So we have a chiral center. Now this molecule overall, it doesn't have symmetry. So if it doesn't have symmetry, the molecule overall is chiral too. So we have a chiral center and a chiral molecule. If it doesn't have any chiral centers, then the entire molecule is achiral. But now what about this example? Let's say if there's 2 bromine atoms. Here we have a chiral center because that carbon has 4 groups, and the same is true for this one. So therefore we have 2 chiral centers, 2 chiral carbons. But what about the molecule as a whole? Is it chiral or achiral? So notice that we have a line of symmetry. So even if we have chiral centers, if the entire molecule is symmetrical, then the molecule is achiral. But the carbon atoms are chiral. Consider this molecule. determine the number of chiral centers that is found in this molecule. And at the same time, calculate the number of possible stereoisomers in this molecule. What is the maximum number of stereoisomers that we can draw for this molecule? So let's identify the chiral centers. The first thing I will look for is a tertiary carbon. Primary carbons are not chiral. Secondary carbons are usually not chiral unless there's like a special group attached to it, like a bromine or a chlorine. So here we have a tertiary carbon, and all four groups are different. Here's a tertiary carbon, but it has two methyl groups, so it's not chiral. This is another chiral center. We have the OH, the carbon atom on the left, the carbon on the right, and the invisible hydrogen atom. This is another chiral center. Here's one. These two tertiary carbons are chiral. This one is chiral, that's chiral, and this is chiral. This carbon atom is not chiral because the methyl groups are identical to each other. So therefore, we have 8 chiral centers, or 8 chiral carbons. So with that information, how can we calculate the number of stereoisomers? It turns out that the maximum number of stereoisomers that can be drawn for this particular molecule is equal to 2 raised to the n, where n is the number of chiral centers. So it's 2 raised to the 8th power. So what exactly is 2 to the 8th power? Well, 2 to the 8th is 2 to the 4th times 2 to the 4th, because 4 plus 4 is 8. 2 to the 4th power, that's 2 times 2 times 2 times 2, 4 times, which is equal to 16. And 16 times 16 is 256. So 2 to the 8th power is 256. So we can draw up to 256 stereoisomers. Now, chiral centers can have a designation such as R or S. So let's say if there's 2 chiral carbons, that means that it's going to be 2 squared, which is 4 potential stereoisomers. Now, a chiral center could be RS, so it can be R for the first chiral carbon and R for the second, or it can be RS, SR, or SS. These are the 4 possibilities if you have 2 chiral centers. Now, let's say if you have 3 chiral centers. The number of stereoisomers is now 2 to the 3rd, which is 8. So you can have RRR, RRS, RSR, RSS, or SRR, SRS, SSR, or SSS. So as you can see, there's 8 possibilities. So now you need to know how to assign the configuration for a chiral carbon. So you need to determine if it's R or if it's S. So let's say if we have this compound. So we have the hydrogen on the dash, and this carbon has 4 different groups. So it's a chiral carbon. What is the configuration of the carbon? Is it R or is it S? So the first thing you need to do is assign priorities to each of the 4 groups. Now, the element that has the highest atomic number is the one that's going to have a higher priority. So looking at the first atoms that are attached to carbon, hydrogen, carbon, fluorine, and chlorine. Out of these 4 elements, which one has the highest atomic number? It's going to be chlorine. So you can look this up in a periodic table. Chlorine has the highest atomic number, so it's going to be number 1. Fluorine has the second highest atomic number, and then it's carbon, and hydrogen is usually the last one. So if group number 4 is in the back, you can count it, starting from 1 to 2 all the way to 3. So going from 1, 2 to 3, the rotation here is, this is counterclockwise, and for counterclockwise rotation, this is going to be called S. For clockwise rotation, it's called R. So what about if hydrogen is not in the back? Let's say if it's on the wedge and if it's in the front. what do we do now in order to figure out if it's R or S? So let's assign priorities first. Oxygen has the highest atomic number. So out of the first atoms that are attached to the carbon atom, oxygen wins. So this is number 1. So now between these two carbon atoms, they're identical. So you move on to the next one. Here we have a carbon, but here we have an oxygen. The oxygen wins for the second atom in the series. So this is going to be number 2. That's number 3. This is number 4. So you would count it from 1 to 2 to 3. Ignore 4 as you go from 1 to 2 to 3. So this appears to be R because we're rotating it clockwise. However, because H is in the front, you need to reverse it so that H will be in the back, and so the proper designation is S. So before you assign before you determine if it's R or S, make sure that group number 4 is in the back. If it's in the front, you have to reverse it.